Okay, it's 9:40 and welcome back, so let's get started. So, 2 announcements. Quiz 7 will be out tomorrow, due on Saturday as always, and we're returning the midterm in class tomorrow. And since Dr. Coburn won't be here, I thought it would be a good idea to go over the solutions of the midterm, just to give you a feel for what we were expecting. And yeah, it was a giant pain putting these back together, but they're all stapled and everything is all good. Hopefully. There's some problems, but hopefully they're all good. Any questions before we start? Any questions about me? So the midterm went well, didn't it? Yeah, something like that. It started off at 50.03 and then went up to 50.2 currently. Yeah. The high was an 89 and the standard deviation I think was 12. I'm not sure. Yeah. Any other questions?
Will it be curved?
Will it be curved?
Yes.
If the grades are up here or down here, it doesn't matter. Look for natural breaks in the distribution. That's the cutoff. Any other questions? Okay. So, what did we talk about, I guess, 2 weeks now ago? If we can cast our minds past all the fun and all that good stuff in spring break. What did we do before that? PDA. Yeah, PDA. So what are these PDA things?
State machines with the set.
Yeah, but what are they called? The push down the tom. Okay. So push down tom. So what was suggested is it's an NFA or a DFA with a stack. But how do I define that formally? Well, how many pieces did an NFA or DFA have? 5. So how many do you think this has? 6, because it has the stack part of it as well. So since it's a natural generalization of a DFA or an NFA, I should have states, input alphabet, skip 1, transition functions, start state, final states. But I want to be as general as possible, so I should allow you to put whatever you want on the stack. It doesn't have to be the same as the input alphabet. You can put on totally different things. So I'm going to make another alphabet called the stack alphabet. Okay. And it's not required that sigma and gamma be the same or totally different or anything. They can be the same or different. Okay. Well, let's see. We know what states are, that's good. Input alphabet, that makes sense. Stack alphabet makes sense. Skip 1. This is a state of the machine, that makes sense. This is a subset of a set of states, that also makes sense. So I think this is the one that we really need to talk about. So, transition function. Well, what thing are we talking about here? We're talking about a stack, right? So, what can we do with the stack?
Push and pop.
Push and pop, right? Should I be allowed to say peak at the top and not ever change the stack contents? Well, I could, but could I do that with pushes and pops? Yeah, I can push an arbitrary symbol, then pop the exact same symbol. Okay. So let's see. I only need to push and pop here. So let's see. Since I have states, I'm going to be transitioning between states. So I better have to be in some state. That's non-controversial. Am I allowed to, on a transition, read a symbol? Yeah, it's just like a DFA and NFA. Could I have a transition where I do not read a symbol from the input? Yeah, it's like an NFA. Yeah, so how did we indicate that with an NFA? What we did is we said you can read from the input if you like, or you can take an epsilon transition. Okay? It's exactly the same thing as NFA here. But we have the stack alphabet to worry about. Oh boy, so how am I going to encode pushes and pops into a transition function? Well, we can't have them occur at the same time, obviously. So we gotta think, which operation should I do first? Should I do pushes first, or should I do pops first? I should do pops first. And why is that? What if I wanted to do a transition that pushed and popped? Which one should I do first? I better do pop, right? If I push something, then it's all not at the top of the stack anymore, the thing I wanted to pop. So I'm already stuck at that point. So we gotta pop first. So, let's see. Should I be allowed to pop something? Yeah, just like we were able to read something. Should I be able to pop nothing? Yeah. Just like here, let's do that generalization as well. So I should be allowed to pop something or not. So let's just be clear. This guy is the pop part of the transition. Okay. Okie doke. What are we gonna do next? Well, we have a state. I think we need to go to another state, right? We better go to some other state. And we gotta handle pushes after we handle the pops, right? Should I be allowed to push nothing? Yeah, like before. Should I be able to push nothing? Yes. So I should be able to either push something or nothing. So let's just remind ourselves this guy is a push. Okay, well, let's see. How many, if I just left it like this, how many states can I go to via this? I'm in one state, how many states can I go to? Can I go to 0? Well, it says that I have to go to something of Q. As is, I can only go to exactly one state. But I need to handle, okay, maybe I could go to 0 states or more than 2 states. How am I gonna handle that? Well, how did we handle it with NFAs? Power set, right? So maybe we can do the same thing here. Let's just do the power set of this guy. So now it says, if we're in a state, read a symbol or not, pop a symbol or not, then I can go to as many states and push whatever I want as I want. Okay? I can go to 0, I can go to 1, or 2 or more. Okay? Good. Any questions about this? So the most important thing here is that pop occurs before pushing in our definition. Nice. So let's actually make a PDA for self. So here's a language that I'm considering. It's not quite A to the n, B to the n, where n is at least 0. I require n to be even here. Okay, well, let's see. How am I going to do this? Well, let's see. If I have a string that looks like this, it's a bunch of A's, an even number of them, followed by a bunch of B's, an even number of them. Well, how did we handle 0 to the n, 1 to the n, where n is at least 0, not the even part? How did we handle that? Well, the idea is, as long as we're reading zeros, we push them on top of the stack. So the stack, when we finish all the zeros, contains the same number of zeros as were at the beginning of the string. Then as long as I read 1s afterward, I'm going to pop the stack in turn, right? Until, could I check if the stack is empty? Ooh, Can I check if the stack is empty? I can't just via this definition, but I can push a special symbol because I can require the stacked alphabet be different than the empty alphabet. Ah, okay. So maybe what we can do for this problem is, instead of pushing one A at a time, I push two A's at a time. And then when we get to the B part to match up with the A's, I pop two B's at the same time. Okay? So let's go over, just as an example, the A to the N, B to the N, where N is at least 0 form. So this is not this language, obviously. But how am I going to make a PDA for this map? Well, what was suggested is, let's push a special symbol on to indicate, okay, we're at the very bottom of the stack. Oh, so that's a good question. What does the stack start as when I fire up the machine? Does it have anything in it? No, so the stack always starts empty. Do I require it to end empty when I accept?
Yeah.
There's nothing in this definition that says the stack has to be empty when you accept. Or when we defined accept in computation, we didn't require the stack to be empty when we accept. But when we start, it must be empty. So if I have a start state here, the stack currently is empty right here. And so as the suggestion was, let's push a special symbol on it. So how am I going to indicate that on the transition? Should I read anything on this transition? No, because our function of this machine is read A's and then push them on at the same time. But I'm not pushing an A here. So I shouldn't read anything. Should I pop anything? No, what would happen if I popped here? Yeah, the machine would completely stop. So I need to not not pop anything. But am I going to push anything? Yeah, some special symbol. Well, it better not be an A or a B. It must be different than one of those. So a common convention is to use a $sign, but you can use any symbol other than A and B in this case. Okay, well, let's see. What was our function of the A part at the beginning? Well, as long as I saw A's, I'm going to push them on the stack. Because when I have a bunch of A's on the stack, I'm just going to match them up when I start seeing B's. And if they're all matched up correctly, what is the only thing I can see on the stack then, if I matched them up correctly? The $sign. So, and that's how we would check that we did everything correctly. So this state right here is going to function as read an A and push an A at the exact same time. So I'm going to essentially just loop in this state because that's, as long as I keep reading A's, I'm going to do the same thing over and over. So should I read anything on this transition? Yeah, as long as I'm reading A's, I'm going to push an A. So as long as I'm seeing A's, I'm going to read an A, obviously. Should I pop anything? No, because I shouldn't, because the only thing on the stack is a $sign, and if I pop, then the stack will be empty, and then I'm stuck after that. So I shouldn't pop anything on that transition. Should I push anything?
Yes.
Yeah, the A at the same time. So as long as I'm seeing A's, the stack is just going to keep growing with A's on it. And then, now I need to decide, okay, the B part is going to start next. Okay? But I can't just read a B on this transition. Why is that?
So you only want to be off?
What's that?
No, you want to be off from the A stack?
Well, I could pop an A at the same time right here. What string is in this language? Where N is 0, which is the empty string. And if I read a B here, then I'm stuck. So I better have a transition where I don't read anything. And since I don't read anything, I better not push or pop anything either. So it's going to be not read, not pop, not push. my term. I call this a triple epsilon transition, but you can call it whatever you want. So all this transition is saying is that when I'm doing the A's, I'm going to non-deterministically guess, okay, the B part's going to start here. So this state is going to represent, as long as we keep reading B's, pop an A off the stack at the exact same time. So on this transition, should I read anything? Yeah, I'm going to be reading B's here. So I better read a B. Should I pop anything? Yeah, an A at the exact same time. Okay. Should I push anything? No, because if I push something, then the next A I need to get to is below the top, and then I'm stuck. So I better not push it. Yeah, better not push anything. Well, let's see. Dollar sign on. So dollar sign with a bunch of A's on the top once I process the A's. Then when I'm processing the B's, the A's are going to pop off at the same time. If I match them up, what's on the stack? Dollar sign. So the only way we should accept here is if there's a dollar sign on the top of the stack. So I better go somewhere else and say, if there's a dollar sign on the stack, then I better accept. Because that's the case when we actually matched everything up correctly. So should I read anything on this transition? No, because if they matched up correctly, I did all the reading in these looping transitions. So I better not read anything. Should I pop anything? A dollar sign, because that's the only way I can check if something's on the stack. Should I push anything? Well, I could, because I don't require the stack to be empty, but I clean up after my messes, so I'm gonna leave it empty. Okay, well, how am I gonna adapt that PDA for this guy, where n is even? Well, here, our idea was, if there's an even number of A's, maybe what I can do is process 2 A's at the same time, somehow. And then when I get down to here, I process 2 B's at the same time. Okay, let's try that. So let's do the same setup as we did before. Maybe it doesn't work, but let's try it. And then, so I'm going to leave the looping transitions off for now. Okay. Well, can I push 2 things at the same time on the same transition? No, because it just says only one thing could be pushed at a given time, or 0, but at most one thing. So how can I do multiple pushes in one transition? I can't. So what could I do instead? Yeah, let's split it between 2 transitions. Well, our idea was it's going to do a self loop. So since I need 2 transitions, I need one that goes out to some state and then comes back to here. I'm splitting it between 2 transitions. So, and I think we're going to do the same thing on this guy too. Okay. For this transition, what should we read anything? Actually, for both transitions, should we read something? Yeah, because we're going to be reading 2 A's in the course of doing this loop thing. So I need to read in both of them. Should I pop in either of them? No, because the same reasoning is there. I should never pop. So it's not going to pop on either transition. Should I push on either transition? Yeah, I better push in the same manner as I did here. For every A that I see, I better push it. So I saw an A in this transition, so I should push it. Saw an A in this transition, I should push it. Okay. What about these guys? Are they going to read something on each transition? Yeah, what are they going to read? B on both transitions. Okay. Should they pop on either transition? Yeah. here it's just basically just 2 copies of this transition. So I better pop on both transitions. Should I push on either transition?
No.
No, I shouldn't. Okay. Well, let's check we did it correctly and I'm not deceiving you. So I start off with a $sign on the stack. If I have an even number of A's at the start, what state am I in? This one or this one?
This one.
This one, right? Because if I have an even number of A's, I read one, then I read another, so I have an even number. So if I have an even number of A's, which is what I want, I'm in this state. If I have an even number of B's afterward, I'll be in this state if I started here. So I non-deterministically guess here, and if I have the same number of B's as A's, I'm going to not only end up here, but what's going to be on the stack? $. So I go here. Yeah.
Do you even need a second state of the B?
I do because I can't push or pop multiple things on the same transition. If I just did this, I may have an odd number of A's and B's. I need to check if it's even. This is for this problem, this one's for that one. Yeah.
So when it's doing like the switch from A's to B's, if you have that epsilon left on position, so could it be that it just, like when it's at checks you, could it be that it just stays in the A state for like a while before actually taking it? Like it doesn't automatically take that one position? So it depends.
It's non-deterministically guessing. So if there is a way to accept, it will choose this one. Or choose this one.
So it wouldn't be able to take the A ones because there's no more A's, so then it would just choose to take epsilon then?
Yes. Yeah. Good question. We'll actually talk about something eventually called deterministic PDAs. I believe this is a deterministic PDA, but we'll get to there eventually.
You could never transition to the B cycle if there were an odd amount of A's, right?
Yeah.
Because you'd be in the second state.
Well, actually, if there were an odd number of A's and I haven't processed them all, I could be here, and I could choose to come down here, but I couldn't apply anything afterward. Because if there were an odd number of A's, then there's no way that I could have popped everything correctly to have the $sign. So, yeah, because there would still be an A on the stack. So, any other questions? Cool. So let's do the second one. It is, I want all the strings such that either it's all A's, consists entirely of A's, or essentially this problem. So, how do you think I can handle that? But it's not concatenation. What's the important word here? Or. What does that correspond to? Union. Oh, could I do union with PDAs? Yeah, how would I do that? How do you do it with NFAs?
Epsilon transition from start state.
Yeah, so if I have a start state, whatever machine's up here and whatever machine's down here, I have an epsilon transition on both of them. But I need to worry about the stack here. Should I push or pop anything on these two transitions? No, because for the machines that I'm going to put here and here, I got to think, those machines are thinking they're starting with an empty stack. So when I go over to them, or whichever one I take, I better not change the stack. It better still be empty. So I better not pop or push on either transition. Okay? Well, the nice thing is that this problem is the one we just solved. So what I'm going to do is I'm going to put a black box right here and put number 1 there. Because there's no need to redo what we just did. But we don't have a PDA for consisting entirely of A's yet. So how can I do that? Do I need a PDA for this? No. How can I get away with that? Or how would we do it with an NFA or whatever? Do I need a dead state with PDAs? They're non-deterministic. So I don't even need a dead state. Ah, so that's even nicer. So here, I can just loop here. Read an A. Do I need to push or pop anything? No, because I'm already in the accept state. I'm never going to leave. So I'm just going to leave this static one. But the most important thing here is that what did we just show about the languages PDAs recognized? Are they closing or something? They're closing their union. Ah, so that's actually very useful. We can just copy and paste PDAs like this, no problem. Any questions about that? Okay, let's do the next one. So, I'm going to need to. So, it says we have a CFG, where this is the start variable, and A 3 A's or A produces BACS, or and it says convert it into an equivalent PDA. How in the world am I going to do that? What's that? Well, this language may or may not be regular, so I can't necessarily apply the same idea here. Let's see. Well, suppose you looked at a string that was derived using this grammar. Could I mimic that derivation on the stack? Well, let's see. Let's just start applying rules. I don't have a string in mind, but let's just start applying rules. So let's say I take S to the A's. So this produces AAA. This guy produces, so I have to choose one of these. Which one do you think I should choose to replace with? A leftmost one, yeah. So leftmost derivations are really going to help here. So let's say I replace that with BACS, with AA afterward. Then I need to, let's say now I applied A goes to empty, so I'm BCS, AA. Then now S is the leftmost variable, so let's say I apply S goes to AA, BC, AA, AA. And then let's say that I apply A to empty on each one of these. So then I have two A's, then I have one A, and then I have no. BCA. What's that?
How do you get from BA to BC?
Which part?
Yeah, that part.
Yeah, so from here to here?
Yeah.
Yeah, I applied A to empty.
Oh.
Yeah. So, well, this is a derivation of a string BCA. Could I mimic this on the stack? Well, let's see. If we mimicked it on the stack, then let's see. Well, if we mimicked it on the stack, then S has to be on the stack because it's part of the derivation. So let's say that S is on the stack. And then after I apply this rule, what should be on the stack? 3 A's, right. Should the S still be here? No, because what we're doing is replacing one variable with stuff. So this S shouldn't be here on the stack anymore. So I'm going to ax him, and then I'm going to put the 3 A's on. Why was it important that we consider leftmost derivations?
You're going like
Ah, yeah. So the leftmost variable is on the top. Can I access anything else other than the top of the stack? Ah, so that's why we care about leftmost derivations. When we convert them to CFGs to PDAs, the variable's on the top. Okay, well, let's do one more, or at least one more. Well, these two bottom A's I'm not touching because they're not at the top of the stack. But I replaced this top A, so I'm gonna axe him. I replaced him with BACS. So what order should I put them? Should I put the S on the top or the B part on the top? The B part, right. So I would have, so I push these in reverse order. So B, SC, A, B. Oh, wait, there's a terminal on top of the stack now. What am I gonna do? I can't replace it with anything. What am I gonna do? Pop? Pop it, but what else am I gonna do along with that?
Read it, so keep track of the string we're trying to recognize.
Yes. So I remember PDAs have an input that they need to match up. So all I'm going to do here is, if the terminal is on the stack, I'm going to read it off of the input and pop it at the same time. If there's a variable, I'm going to do a replacement with some rule corresponding to it. Cool. So let's actually convert this PDA, this CFG to a PDA. There's a problem. You know what the problem is? If I just did it blindly like this. How would I know if I matched everything up correctly? What if there was some input still left and the stack's empty? If I tried to pop while reading something, then the machine stops. I don't want that. So how am I going to remedy this? Use a special symbol, right? Just like we did with the now erased examples. What we should do is push a special symbol, say a $, on the bottom, so that if I ever run into a situation that I've matched up part of the input and there's still input left, the stack will never be empty until I pop that $. So if I can't apply a transition, I can't ever run into a situation where I pop an empty stack. So I should push a special symbol on at the beginning, and then when I matched everything up correctly, pop it at the end. Nice. So let's make a PDA for this guy. So what is the very first transition going to do then?
Push the $.
Push $. Nice. So no read, no pop, push $. So this is going to go to some state. What should I do after that? So $signs on the stack, what should I put on next? The start variable, right? Because we have to start the derivation somewhere, and what better than the start variable? So S is the start variable here. So I'm going to push on the the start variable as well. Cool. Well, let's see. What do you think the function of this state is going to be? Well, we got to have some place where if there's a terminal on the stack, we're going to pop and read with the input at the same time. Or if there's a variable on the stack, we got to apply a rule application. So we need some place to do that. What better than here? Because now there's a variable on the stack, the start variable. So we got to apply a rule for that. Okay, so let's make that the state that we want to do both of those things. So let's do the easy one first. The one where if there's a terminal on the stack, we're going to read off of the input at the exact same time and pop it off the stack, obviously. So what are the terminals of this grammar? Lower A, lower B, lower C. So how many transitions am I going to add here? 3, right. One for each of the symbols. So they're going to come from this state. Where are they going to go? Well, once we pop a symbol off the stack and read it with the input, I'm all done with that particular step. There may be another terminal, but as long as that is concerned, I'm done. So I think this is a self loop. Okay? So I'm going to have 3 self loops for each of those 3 cases. So let's say that we see an A on top of the stack. What should I do? Should I read on that transition? Yeah, I'm reading off of the input while I'm popping up the stack the exact same symbol. So I should read A, right? And pop A. Should I push anything? No, because if I pop something, then there may be another terminal, and then I'm just gonna create more work for myself. Okay, well I think the B and the C terminals are gonna work exactly the same way. Because if I see them, I wanna match it up with the input. Okay? You see how we're doing that part? Well, the only other case is that we see a variable on the stack, or we see the $sign on the stack. So let's handle the variables first. Well, the only 2 cases are I see an S on the stack, or I see an A on the stack. So let's handle the case where I see an S on the stack. Well, what are the only transitions that are going to read here? Should I read on anything other than these self-loop transitions? No, because the only time I read is when I produce a terminal with the derivation. I shouldn't ever read any other time. So this transition better not read. But I said that we see an S on the stack, so I better pop the S off, and then we're going to worry about pushing in a second. But for right now, I see an S on the stack, I'm going to pop it off. So now what do we got to do? Let's say that we wanted to apply a triple A right here. What order should I push everything on? Should I push it this way or this way?
Right to left.
Right to left, right? Because, for example, it doesn't matter for this one, but for this one, it matters because I want this B on the top. So I should push S first and then go this way. But for this one, it doesn't matter, obviously. So since I can only push one thing on the stack at a time, I think I need 3 transitions. So what I'm going to do is have a transition where I don't read, don't pop, but push an A 3 times. And then I'm just going to follow the construction we did in class, which is slightly different than what I'm used to. And then what we're going to do here is, once we push these 3 A's on, I'm just going to triple epsilon back. It's not strictly necessary to have this here, but it's just useful to have. Because you can separate the logic of what things you're pushing versus the state that actually does the work that you come back to. But this transition is not necessary. Okay? Cool, but that's exactly what we want. We're taking the S off the stack and replacing it with the right-hand side in reverse order. Cool. So this rolls down. Now we got to apply an S to AA. And so I'm going to not use this transition again because I want to separate each of the cases, all the rules separately. And so this is my least favorite part about drawing these is that everything gets in play. So let's see, where do I have room? So I'm going to come down here. Well, on this transition, I better still pop the S off the stack because it's still in the stack in this case. But I need to push these on in reverse order. So which one should I push first? The big A, right? And then little A after. So I'm going to have 2 transitions, not read, not pop, push the big A first, and then push the little a second, and then triple epsilon back in. Okay? So that guy's done. What about this guy? Well, let's do the a to epsilon first because that's easier. Well, I need a state that I go to that I read nothing again, pop an A, and push nothing. But what is this state going to do? Where's it going to go on anything? I'm doing A to epsilon. Just come back, right? I don't need to push anything on because it's epsilon. So I just transition back to the state on triple epsilon. Super. So this roll's done. Now I gotta do A to BACS, the long guy. Okay, so I'm good, I left myself some room. So on this transition again, we're gonna have A popped off the stack. And then again, I gotta push things in reverse order. So what thing should I push first?
S.
S, and then C, A, B. Cool. So I should have no pop, push S, epsilon, epsilon, C. Okay. Yeah. Epsilon, epsilon, A, epsilon, epsilon, B. And then triple epsilon. Cool, so this roll. Am I done? I need a file state. The language of this thing is empty right now, right? Because there's no accept state. So when should I accept? Well, let's think about it. If we did a derivation correctly, then, and we matched all the input up with what appeared on the stack as terminals, then what's on the stack currently? The $, but what state am I in? Yeah, this third state. So I need a transition where I detect that the $'s on the stack, and I'm in this state. Oh, so therefore, I need a transition from here on. Should I read anything on this transition? No, because the only transitions that should read are the ones where I produced a terminal. So this one shouldn't read either. But I should pop the $' off because that's the only way to detect that. And it doesn't matter whether I push anything. But I should accept nonetheless. So let's just figure out how all this works. So $' on the stack, S on top of it. So a $' with a variable. As long as there's a variable, I apply one of the rules in reverse order. And then if there's another variable, I apply a rule for that guy. But if there's a terminal on the stack, then I just match it up with the input. So the only way we could have matched up everything correctly is if there's a $' left, and therefore we accept. Okay? We could go here without having read all the input, but should I accept at that point? For example, if the input string was A, and we applied, if there was a rule S goes to empty, then I can just make this S disappear. There's only a $' now, and I can go here, but have I read all the input? No, because S goes to epsilon. I didn't apply one of these reading guys. So I could go to the accept state and not having read anything, or read all the input, but should I accept at that point? No. So the only way I could accept there and stop is if I've read all the input. And the only way I could have done that is if I read them via these transitions, but the only way that these could have come about is with a rule application. And so we just did a derivation using the stack. That's pretty cool, isn't it? So we can actually convert any CFG in this manner to a PDA. Any questions about that? Okay, we have a little bit of time. So let's do the fourth question. So let's say that, so I don't know what this PDA looks like, but let's just assume it's a black box with some set states in it. And what we want is, x pound sign y with x and y in the language of the PDA. So I'm given this PDA P as a black box. I want to know, can I make a PDA for this? And pound sign is not in the input alphabet. So can I make a PDA for this guy? Is there any dependence on x and y to each other? No. So what do you think this is? Well, it's any string that the PDA can make. Pound sign, any string that the PDA can make. What does that look like? It looks like concatenation. So can we make PDAs be closed, or the languages of PDAs be closed under concatenation? So that's what we want to answer. Well, it seems pretty clear that we need 2 copies of our PDA. So I'm going to have 2 copies of our PDA. Let's say it has 2 accept states. So this is P, and here's another copy. P, 2 accept states. Let's see. Think about how the PDA starts up. Is the stack empty when the PDA starts up? Yeah, it's empty when it starts up. So if I just looked at x by itself and not considered that, if I looked at x by itself, the PDA for it assumes the stack will be empty when it starts. What about here? If I just assume y, that's the exact same thing. So I can't just blindly do concatenation here, because the PDA could have a non-empty stack when the first one finishes. So we need to be aware of that. Well, let's see. What are we going to do about this? Well, what are we going to do? So if we're in this state, we need to read a pound sign, right? So if we're in this state, we need to be able to read a pound sign. Should I pop anything on that transition? No, right, because it could be empty right now, or it might not be empty right now. So I need to be able to read it, not pop, not push. Not read, not pop, not push. So I go to this state. And what do you think this state's going to do? Epsilon transition in. So that seems like a good idea. It'll turn out not to work entirely. Well, let's think about it for a second. What is this PDA expecting for its stack to be at the start? To be empty. Do I have to have an empty stack when I accept? If it's not empty here, will it be non-empty when I get here? Yeah, it will be non-empty. So how can I handle that?
Stick a loop at a state.
Well, I could make a loop. So let's say that the alphabet is, okay. So let's make a loop for not reading, pop the A off, epsilon for each A in the stack alphabet. That'll certainly help, but I have run into a problem. How do I know that the stack is empty? But because if it wasn't empty, there may be another way to accept a different string in here that I didn't want before. So how can I handle this? Maybe I can, at the start here, push on a special symbol, and here, pop that special symbol on. So that's what we're gonna do. New start state. I better not read, better not pop, push a special. So I assume that $ is not in the stack then for now. Of this modified one, it certainly is, but not of P. Okay, well, let's see. Then once I get to here, I need to get to here, but I'm expecting an empty stack, and the only way that that can happen is if I pop it off right there. Cool. So there is a little bit of extra care that you have to be aware of when you're doing concatenation, because the PDA is expecting an empty stack when it starts. So you have to handle that, but it's not very hard to do so. Any questions about this?
So will there be $2 signs like when we go inside this?
I assume $ not in any of these transitions. I assume it's not in the stack alphabet.
So there will be two symbols like.
I'm adding an additional symbol to the stack alphabet for this modified PDA. Any other questions about this? Cool, I'll see you next week.